remind myself to start this. A couple things to note. I've uploaded 2 homeworks. So I've done homework number 6, that's chapter 6 homework, as well as homework number 7, which is what we're talking about right now. So those are available for you guys to look at and attempt to answer the problems. They have a due date right now of the Sunday before the exam. So it's like the 21st, okay? That's at midnight, the Sunday before the exam. So make sure to try to get to both of those before the exam or before midnight when they're due, of course, before the exam, okay? So what we're going to do today, we're going to talk about Chapter 7 and the remainder of what I have to talk about with respect to Chapter 7. And then next week, we're going to move into Chapter 8. And we're going to take the 2 class periods next week to talk entirely about Chapter 8, which deals with enzyme kinetics, okay? So the material that we cover next week is unfortunately going to be on the exam, okay? So just note that we are going to actually go over that material next week, and then it will be presented on the exam on Tuesday. And I'm sorry about that I'm kind of running out of time. With that said, I have also uploaded a practice exam for this exam. Hopefully you guys have seen that. Has anyone looked at that yet? I did it last night, so obviously probably nobody has. So just as a reminder, exam number 2 is going to come in 2 parts, right? We're going to have the amino acid part first, right, where I give you either the name or the single letter abbreviation or the 3-letter abbreviation, and you guys have to draw the structure. You guys are going to turn that part in, and then you're going to take the multiple choice part, okay? So just be prepared for that. That is what is coming in a week and a half. Okay, are there any other questions? No. Okay, so we're going to go ahead and get started. So we're talking about myoglobin, right? That's what we were talking about however long ago it was. So myoglobin and its binding to oxygen, right? So we had gotten to this slide, and on this slide what we were talking about is the fractional saturation curve for myoglobin, right? So fractional saturation we defined, so we'll go ahead and draw this as the fraction of myoglobin molecules that have oxygen bound to them. So this is the number of myoglobins that have oxygen divided by the total number of myoglobins. Okay? And so the larger the fractional saturation, the more myoglobins have oxygen bound to them. The smaller the fractional saturation, the less the myoglobins have oxygen bound to them. Okay? And so for myoglobin, we had derived this little expression where we could relate this fractional saturation to both concentration as well as partial pressure of oxygen, okay? So we had derived this little expression where we had this fractional saturation as the partial pressure of oxygen divided by what we called Kd. What was Kd? It was an equilibrium constant, but what was it for? Dissociation, right? So dissociation of myoglobin from oxygen plus the partial pressure of oxygen. And so we get rid of this guy, Kd, at this point in time, and instead we relate this, Kd, to what we call this P50, okay? So Kd is numerically related to the partial pressure at which 50% of the binding sites are taken up, and that's what P50 is supposed to be related to, okay? Okay, so P50, Kd, these are both kind of measurements of affinity for something. Affinity for binding oxygen to myoglobin, okay? All right, so we can also represent our fractional saturation via what we call this fractional saturation curve. And when we see something like myoglobin, which has a single binding site, what we're going to see for that is something that is hyperbolic, okay? So we get this beautiful little hyperbolic curve. At high partial pressures, where pretty much all of the binding sites are taken up, this is where we refer to saturation. So at high partial pressures, pretty much all of the binding sites are occupied, and so we are saturated with oxygen. And as we move down to lower partial pressures, we're going to start to see some of these binding sites releasing their oxygen so that we're going to get these fractional saturations, okay? All right, so one thing that we can look at with respect to the affinity of these binding sites for oxygen is the steepness of this hyperbola, okay? So the steeper this hyperbola is, or the steepness before we reach saturation, the greater affinity there is for oxygen. So steeper the hyperbola, greater affinity for oxygen, or any type of small molecule binding, and this translates into a smaller value of P50 as well as KD, because these guys are numerically equivalent for one another. Okay, so the greater the affinity, the smaller the P50, the less the affinity, the larger the P50. Okay? And so for myoglobin, at the very end, I had given you what P50 was. And so for myoglobin, what was P50 in torr? I don't like to measure things in mmHg. So P50 for myoglobin, very last part of class I had said was about 2.6, 2.8 or 2.6, 2.8. And this was torr, right? So again, for myoglobin, this is the partial pressure at which half of the binding sites are occupied, okay? So it's fairly low partial pressure. Okay, so that is myoglobin. I think we've covered everything that we had already covered. So again, as just a little note for later on, this hyperbolic binding curve is going to be distinguishable for any type of molecule or any type of enzyme where you have a single binding event, okay? So this is going to be very similar to when we're dealing with enzymes that only have a single active site, or any type of other molecule that has a binding, but it only is going to bind one single molecule. So this guy is indicative of what we're going to call non-cooperative binding. Okay, so myoglobin, that's great. We're going to move on now to hemoglobin. So hemoglobin is a little bit different. We're going to start by talking about the structure overall of hemoglobin, which we have already talked about thus far when we talked about quaternary structure. Okay, so hemoglobin is also a globin. What is kind of the secondary structural feature that is going to characterize our families of globins? All alpha helical, right? So all globins are all alpha helical. Hemoglobin is no exception to that. So hemoglobin, as opposed to myoglobin, is a multi-subunit protein. Okay, so hemoglobin is multi-subunit. It is a heterotetramer. Okay, and so its heterotetrameric component is an alpha 2 beta 2 structure. So it has 2 alpha subunits, 2 beta subunits, and again, they associate together. Okay, each of those subunits has a heme. Okay, so each of those subunits has an oxygen binding site, because remember that oxygen is going to be binding at the heme. So just as a reminder with respect to heme, we have an iron that's in the +2 oxidation state. It is octahedral, so how many different bonds can this iron form? 6 different bonds, right? And so 4 of those come from what? The nitrogen in the porphyrin ring, right? So we have that nice little pretty planar porphyrin ring. So 4 of those are coming from the nitrogens in that ring. What is the 5th binding site coming from? Same thing with respect to myoglobin. We're going to see the same thing in hemoglobin. There was a histidine that was very important, right? So the imidazole side chain on a histidine. And what did we call this histidine? Because it was in the F helix of myoglobin. This was F8. So this was our histidine F8. It was also making the nitrogen from the imidazole side chain, was making a bond to iron. And then who is going to be occupied by that 6th site? Oxygen, right? So oxygen was going to come and bind at that 6th site. We have the exact same structural features in hemoglobin, okay? Now, we just have 4 of them because we have 1 in each individual subunit, all right? Okay, so, again, hemoglobin is a heterotetramer. It essentially associates in an alpha-beta unit, so this is what we would call a protomeric unit, so we can consider this a dimer of alpha-beta protomers. So the alpha beta is kind of like the structural unit that we see a repetition of. Okay, and so with respect to each of these subunits, we're going to see these guys coming together and obeying the exact same things that we could expect for subunits coming together in a quaternary fashion. So we're going to see a lot of non-covalent interaction between the interfaces of the various units. We're going to talk specifically about those non-covalent interactions in a second. All right, so P50 for hemoglobin is slightly different. And we're also going to talk about the binding curve for hemoglobin because it's also going to be different. But we see a order of magnitude increase in the P50 for hemoglobin comparatively to myoglobin. So P50 for hemoglobin ends up being about 26 torr. Okay, so one more thing I forgot to mention before. Alpha and beta, which again are making up the exact same protein, so this alpha subunit, beta subunit, these guys are all structurally as well as sequence-wise related to one another. Okay, so alpha beta actually share about a 30% sequence similarity with respect to one another. They are also evolutionarily related to myoglobin. So both of those share about an 18% sequence similarity to myoglobin. And structurally, they are pretty much indistinguishable. Okay, so let's think about what hemoglobin does. What does hemoglobin do? Transports oxygen, right? So it picks up oxygen in our lungs where we have a very high partial pressure of oxygen, and it transfers it out to our tissues where we're going to have a lower partial pressure of oxygen. So what would be very beneficial for this molecule to be able to do with respect to affinity for oxygen as well as being able to release the oxygen when it gets out to our tissues? So in our lungs, we're going to have a very high partial pressure, right? So we're going to want a molecule, if it's going to be very good at its job, which job is what we've just talked about. We want a molecule that's going to be able to bind oxygen very well in the lungs, right, at whatever type of partial pressures we're going to see in the lungs. The lungs end up having a partial pressure of about 100. So the partial pressure of oxygen in our lungs is about 100 torr. We're also going to want it to, when it diffuses out to the tissues, to be able to get rid of those oxygens, right? So in the tissues, the partial pressure of oxygen is about 30 torr. So for this guy to be really good at its job, it's going to need to bind it at a high partial pressure. Then as it moves out to the tissues, it's going to want to be able to release it when we get out to the partial pressures of oxygen in the tissues. Another important thing, too, is it's not going to want to release all of its oxygen, right? Because as we live and breathe and do all of this, we don't necessarily need all of our oxygen at this point in time, right? But if I went and started to run and do a bunch of working out, I need more oxygen, right? So another big important role for hemoglobin is that as we're resting, as we're doing these normal things, it's going to want to release enough oxygen, right? But it's also going to want to hold a bunch of oxygen in case a prey comes in and tries to attack me and I have to run away very, very quickly. Okay, so it's also going to want to store a little bit of that oxygen just in case we actually need it if we were attacked at some point in time. Okay, so this is the idea behind what hemoglobin has essentially been evolved to do. Okay, all right, so now we're going to look at the binding curve for hemoglobin to kind of demonstrate how it has evolved to accomplish all of these tasks. Okay, so if we look over here, this is going to be our binding curve. We have superimposed the binding curve that we saw for myoglobin on the exact same plot. Okay, so again, we're looking at fractional saturation as a function of partial pressure, okay, of oxygen. And so if we look at myoglobin is this little yellow line here, okay, and we compare it to hemoglobin, what we're going to see, so for myoglobin, as we're out here in the lungs, we're at about a partial pressure of 100 torr. Is myoglobin completely saturated in the lungs? If we had myoglobin in the lungs, let's say that. So as we're out here at about a partial pressure of 100 torr, myoglobin at this point in time is completely saturated, right? As we move to the partial pressure values of oxygen in the tissues, which is about 30 torr, what's happened if we had something like myoglobin transporting our oxygen? Very little of it has actually come off, okay? So for myoglobin, this isn't good. So really high affinity for oxygen wouldn't deliver any oxygen to our tissues when it actually got to the tissues, okay? So instead, what we see is this type of curve. This is what we see for hemoglobin, which again is what we're actually talking about, right? Is this a hyperbolic curve? No, right? This is not a hyperbola. What is this instead? This is sigmoidal. So it forms this nice sigmoidal S-shaped curve. So again, myoglobin was hyperbolic, but for something like hemoglobin, this is a sigmoid. It is not hyperbolic, okay? This is a very big indicator if you were to have some sort of sigmoidal-shaped curve of cooperative binding, okay? And we're going to talk pretty much ad nauseum about what that means with respect to hemoglobin. Note, with respect to this sigmoidal S-shaped curve, there are essentially two distinct features on this curve, okay? If we go down to really low partial pressures, as well as really low, very small values for fractional saturation, we have kind of this nice linear curve which has a very shallow slope. What does that tell me about the affinity for oxygen at this point in the curve? It's pretty low, right? So this is what we call our low affinity state. So very few of the molecules are actually bound at this point in time, but in this low affinity state, we don't have a great affinity for oxygen. But then what happens as we start to increase the partial pressure or as we start to increase the fractional saturation? It starts to steepen up, or become much more steep, right? So we go from this low affinity state to what we're going to call this high affinity state. And so again, this shift from low affinity to high affinity is a very big indicator of cooperative binding. And so what does that actually mean? Right, so down here, we had very low affinity for oxygen, right? So we're going to actually have to go to quite a high partial pressure before we actually get an oxygen molecule to bind to our hemoglobin. But once one does, we see this entire shift, right? So everything shifts to this more high affinity state. And so once we have one molecule bound, everything's going to shift to this high affinity state. So it's going to be much easier, a much more high affinity to bind oxygen. Okay, so binding of one ligand essentially shifts all of the other ligand binding sites to be in this high affinity state. And this is essentially what this curve is trying to tell you. Okay, so high affinity state, low affinity state, we have this nice sigmoidal shaped curve with respect to hemoglobin. So now let's try to understand this a little bit better, okay? All right, so again, this is a big, at least this sigmoidal shaped curve is a big indicator of this cooperative binding, okay? So again, cooperative binding is going to be defined as binding as one ligand to a site is going to affect binding of all of the other ligands to the other sites in the protein. And we're only going to be able to see this in these multi-subunit proteins. If you thought about cooperative binding with respect to myoglobin, oxygen's going to bind at one site, but there's nothing else with which oxygen can bind to in myoglobin, right? So that's why we get hyperbolic curves. With sigmoidal curves, though, we have to have multi-subunit proteins so that we can actually see this cooperative binding event. Okay, so let's talk about this in a little bit more detail. So that sigmoidal S-shaped curve was first studied and looked at by this dude named Archibald Hill, okay? And what he did was he empirically modeled the data that he saw, this fractional saturation curve for hemoglobin, to this equation. Okay, so this is the Hill equation. What does it look like that we've already seen? The fractional saturation curve for myoglobin, right? It's very, very, very similar, except it differs in the fact that everything is raised to this H power. Okay, so we're going to call this the Hill coefficient or the Hill constant. And we're going to talk about some of the implications behind this Hill constant, okay? So if H was equal to 1, if the Hill constant was equal to 1, what would this reduce down to? Just a hyperbolic curve, right? So if H was equal to 1, all this would do is reach down to a hyperbolic curve, which is what we saw from myoglobin, okay? So if H is equal to 1 in this expression, then this is very indicative of non-cooperative binding, which is, again, what we saw with respect to myoglobin. All right, now let's imagine H is equal to the number of binding sites in the molecule. Right, so how many binding sites do we have in hemoglobin? So if H were equal to 4, this essentially would say that the minute you bound one molecule of oxygen to one of the hemes, all of the other ones would immediately bind oxygen at the same time. So if H were equal to 4, this is what we would call infinite cooperativity. Which is actually a physical impossibility. Okay, so just note that the kind of two extremes were H equal to 1, which is non-cooperative binding, and H equal to 4, which is infinite cooperativity. What we actually see is something about right in the middle. So H is usually going to be equal to something greater than 1, so something greater than non-cooperative binding, but less than N, which is the number of subunits or the number of binding sites in the protein. And so for hemoglobin, what we see is H equal to about 2.8 to 3. Okay, and this is going to indicate cooperative binding. Binding of one thing is going to make binding of all the other things easier, cooperative binding. There is a possibility that H could be less than 1. What do you think H less than 1 is going to indicate? Negative cooperativity, right? So if we have H less than 1, then we're going to see something where binding of one of the molecules is actually going to make it harder to bind other molecules in the other subunits of the protein. That is what negative cooperativity indicates. And with respect to all of this binding events, this is all a good illustration of what we call allosteric interactions. And this is why I talk about hemoglobin a little bit too much for the most part, is the fact that we're going to come back to these allosteric interactions quite a bit in the remainder of the semester. And so introducing you to what I mean by that now is kind of important. So what is an allosteric interaction? So this binding of oxygen is a good example of an allosteric interaction. It's essentially an interaction where you have binding at one site, a structural shift and change in the protein, which affects binding at all of the other sites. So allosteric has a big important thing. It's the actual structural shift of the protein that makes binding at the other sites either easier or harder depending on the degree of cooperativity. Okay. All right, so let's talk about how this actually happens, right? How does myoglobin, or hemoglobin, transfer the fact that, hey, I've bound oxygen at one site, now you need to make these other sites better at binding, or have a higher affinity for binding oxygen. So we're going to talk about how that actually goes about, that structuring, in a second. Okay, so before we can start that, I'm going to introduce you to this model of symmetry or concerted allosteric, okay? This is also called the MWC model. And there are a lot of different types of models with respect to this allosteric effects, but we're going to focus only on this one, only on this theory of allosteric, because essentially this is how we explain hemoglobin's binding in the protein, or oxygen's binding to hemoglobin. So in this model, what we're going to have is two different states. Okay? One of the states is called T, which refers to tense, and the other state is called R, which refers to relax. Okay? And they are going to be in equilibrium with one another. For hemoglobin, our tense state is what we're going to call our deoxy state. So our deoxy state, where no oxygen is bound, and our R state is going to be called our oxygenated state, or our oxy state, where we have oxygen bound. So we can also refer to these as a low affinity state. So we saw that when we didn't have any oxygen bound, we had very low affinity for oxygen binding. And if we had low affinity for oxygen binding, how would that translate into the P50 value for this low affinity state? So P50 is going to be smaller, right? So low affinity state, not smaller, pardon me. We're going to have a larger value for P50 here. So low affinity state is going to take a lot more oxygen before we actually get to that half fractional saturation. Okay? All right, so the R state is the oxy state. This is our high affinity state. And again, in this high affinity state, this is going to be our smaller value of P50. Okay, so how does this actual concerted model work, this MWC model? How are we going to imagine what's happening in hemoglobin with respect to this shift between T and R, or our deoxygenated state versus our oxygenated state? Okay, So in this model, what we assume is we're at equilibrium, right? T versus R. For hemoglobin, we're going to find that T is actually the much more preferential or stable state. So it's going to essentially be preferred at equilibrium before we have any oxygen molecules coming in, okay? As we get a binding event to our T state, that's going to essentially shift the equilibrium, okay? So as we get oxygen binding, our first binding event to the T state, we're going to shift the equilibrium so that all of the other sites in a concerted fashion shift into the R state, which is again the high affinity state, okay? So it's not that oxygen binds to one and then one right next to it becomes R and then one right next to it becomes R. Instead, it's oxygen binds to one, all of the others shift into the high affinity state, okay? So how could that possibly occur? So oxygen is binding at heme, right? And so we do have 4 hemes in the structure of hemoglobin, but they are about 27 angstroms apart from one another, right? So that's far too far apart for them to be able to say, oh, I've electronically changed, you need to change as well into our R state, okay? So instead, what's going to have to happen is there's going to have to be some sort of structural shift in the protein that takes binding at one site and essentially turns all of the other sites into this R state. So what is that shift? What do we actually see with respect to how this protein has evolved to do that? Because again, cooperativity here is very important with respect to hemoglobin binding oxygen and being able to do its job appropriately. So let's talk about these structural shifts that we see with respect to hemoglobin. Okay, so all of this data, all of these models that we have with respect to these structural changes that occur upon oxygen binding in hemoglobin come back to X-ray diffraction studies, okay? We have multiple structures where we have oxygen in the completely deoxygenated state versus, hemoglobin in the completely deoxygenated state versus hemoglobin in the completely oxygenated state. And there are structural differences and structural changes that we're going to compare to show how this is actually translated or transferred throughout the entire structure of the protein. Okay, so first we're going to start talking about interactions in the T state. All right, so in the T state, if we look at the X-ray structure, so I'm going to zoom in. There are a significant amount of non-covalent interactions that occur between the two interfaces of alpha subunit and beta subunit. Okay, so I'm going to illustrate a couple of those. So number one, at the beta terminal, or the beta terminus, or the C terminus of the beta subunit, we have a very important histidine residue. Okay, so that histidine residue, it's C terminus, because we're at the C terminal part of the protein, is going to make a salt bridge with a lysine, a protonated lysine that is on the alpha subunit next to it. Okay, so that's one non-covalent interaction, a nice salt bridge. And again, this is the C terminus of the beta subunit. Okay, another important little non-covalent interaction that this histidine makes is between its side chain, its imidazole side chain, which is positively charged, and an aspartate on its own beta subunit. So this is an intra-subunit interaction, okay? So we have one salt bridge here, which is inter, between two different subunits, and one salt bridge here, which is inter. Again, this is a stabilizing effect for the T state, okay? All right, so then there are other non-covalent interactions that occur at the alpha subunit. Okay, so one of these really important key residues in this, let me highlight it, is this arginine 41. Okay, so arginine has a nice basic side chain, right? It has that guanidinium group. That guanidinium group has a positive charge at neutral pH. So it makes a bunch of interactions with respect to other residues. Okay, so the positive charge guanidinium group makes another salt bridge. So we look at this guy, we get another salt bridge between an aspartate on a different alpha subunit, okay? It also makes a hydrogen bond between the carbonyl carbon or the carbonyl oxygen on a valine of the beta subunit. This arginine is the C terminus of this subunit, so it also has this free carboxylate group. This free carboxylate group makes another salt bridge with the lysine 27 on alpha 2, the other alpha subunit, and it also makes an intra-subunit little salt bridge with a chlorine ion on valine, or this is the N-terminus of the alpha subunit. So valine 1, which is the N-terminus of the alpha 2 subunit. Okay? So again, these are all extremely extensive non-covalent interactions that help stabilize the T state. When we look at the crystal structure of this protein in the R state, all of those interactions are broken. All of them are gone. Okay, so in the R state, we have none of those stabilizing interactions, right? All of them have been broken, okay? What do you think energetically is going to be paying for breaking all of these inter-subunit or non-covalent interactions, right? We're going from the T state, the deoxygenated state, to the R state. We're breaking a lot of non-covalent interactions in the process. What's going to pay for that energetically? Are we forming a bond anywhere? We are. So what bond are we forming? And moving from deoxygenated to oxygenated. The iron is binding or making a bond with the iron and the porphyrin. Okay, so all of these little non-covalent interactions that we're going to essentially be breaking and making this transition are going to be paid for by the bond that forms between the iron in the porphyrin ring and the oxygen that's binding to it. Okay, so those are our little inter-subunit interactions, our non-covalent interactions that we see in this shift from the T state to the R state. There's also one other little area to indicate. Oh, I totally took it out. Darn it. Okay, we'll come back to that, okay? So these are the important interactions. So obviously I decided to get rid of that other slide. These are the important interactions that we're breaking and moving from the deoxygenated state to the oxygenated state. And again, the entire purpose of talking about this is trying to show you how a protein can translate this information to other binding sites, okay? So number one, it broke all those interactions. How is binding oxygen at one of the hemes going to break those interactions, though? It's going to change the shape. It's going to change the structure of the binding site entirely, which is essentially going to translate to breaking all of those interactions, which is going to translate to turning or changing the binding site in all of the other parts of the protein. Okay? So how does that actually occur with respect to this transition between the T state and the R state in our first binding site? Okay? So we're going to go back to what's happening at heme. We're going to talk about what happens at heme. So just as a reminder, heme is, before oxygen binding, is 5 coordinate. It has 5 things bound to it. It's got the nitrogen with the porphyrin ring. So we have 4 nitrogen iron bonds. So nitrogen iron bonds. And then we also have that imidazole side chain. Okay? Now the problem, before oxygen ever comes in with respect to this heme, is that the bonds, this nitrogen iron bond in the porphyrin, is too long. Okay? So before we ever bind any type of oxygen, this bond is too long. And so because of that, we start off, before binding oxygen, with a heme that's kind of a domed shape. The iron comes up out of the plane of the porphyrin, and it forms this dome-like shape, which is fairly unstable. It's a distorted structure. Okay, so this leads to the doming of the iron in the heme. So because of that, because this iron kind of pops up out of the plane of the porphyrin, that imidazole side chain that's on the histidine, that's part of that F helix, is kind of at a little slanted shape. Ideally, it would love to be perpendicular to the iron, but because that iron's popping up, that little imidazole side chain is slightly slanted with respect to the iron. Okay, so again, we start out in this distorted state. So now, oxygen's going to come in. Just as a reminder, because I'm trying to illustrate all of this, I get super excited. When we had free heme outside of the protein, so heme in the iron 2+ state, and this was outside of the protein, and we introduced oxygen to it, what happened? It oxidized, right? This immediately oxidized to iron 3+, which was irreversible, right? It lost an electron to the oxygen, okay? So now as oxygen comes in, we know that we're not going to oxidize this heme, but instead what's going to happen is that oxygen is going to take a little bit of that electron density. We're going to see partial oxidation, right? As it pulls a little bit of that electron density towards it, it's going to essentially remove a little bit of this electron density in these nitrogen-iron bonds, right? So if we remove a little bit of electron density, what's that going to do to the bond lengths of these guys? It's going to shorten them, right? So they were already too long, but now we're shortening them by partially oxidizing the iron, pulling a little bit of electron density towards us. So what's going to happen to the iron? It was domed beforehand because those bonds were too long, but as we're removing that electron density, what's it going to do? It's going to come into the plane of the porphyrin, which is where it wanted to be in the first place, okay? So as this guy comes into the plane of the porphyrin, that histidine is going to follow it, right? But if it followed it directly down, it would actually crash into the porphyrin ring. So instead, it moves directly into the perpendicular with respect to the porphyrin ring, okay? So again, we get oxygen coming in, pulls a little bit of electron density, our iron comes into the porphyrin ring, and that histidine's midsole side chain essentially shifts and moves into the perpendicular. That's attached to protein, right? That's attached to an alpha helix. If this guy shifts to be perpendicular to the iron at this point in time, what's going to happen to that helix that it was attached to? It is also going to shift with it, right? So that F helix, which is what this little histidine and imidazole side chain is attached to, as this guy shifts into the perpendicular, that F helix is going to move with it, okay? And when it moves with it, it's also going to move its little FG moiety, right? So it's got this little loop where the F helix connects with the G helix. That's also going to shift with it, and it's this FG interface where all of these various electrostatic interactions, all these various non-covalent interactions actually come from. So movement of that F helix shifts FG, which breaks all of those things. What that's going to do, and what that's going to translate into for the remainder of the protein, is all of the remainder of the binding sites are also going to move that F helix, right? Because it's all interconnected. And so if they all move that F helix, then all of them shift into the R state, which is this state where we have the iron in the plane of the ring, and we have this perfect ready binding site for oxygen. Okay, so that's how heme and oxygen binding to heme in one subunit is going to translate into all the other subunits and turning all of the other subunits into this R state. Okay? Okay, all right. So that is the molecular mechanism for this actual covalent, or not covalent, cooperative binding event that we see in myoglobin. Unfortunately, this is only a model. Right? So this is kind of, like, oh, you see the shift and then there's shifts and everything just happens to be perfect at the end, right? So this is a model that is based on structural biology, right? We have structures, and so we present these models based on that. There are also other structural studies or other various studies that have been done to try to help support this model. So one of them was given by the following little experiment, okay? So in this following experiment, what they did is they took wild type hemoglobin, right? And they took that histidine, that F8 histidine, which is super important in the binding to the iron porphyrin as well as moving that F helix. They took that and they mutated it to a glycine, right? So glycine doesn't have any side chain, so there's going to be this empty little binding pocket there. That wouldn't be very good, right? That molecule, just as is, would not be able to bind oxygen because, again, it wouldn't be 6-coordinate. It would be very unstable. So what they did is they added in imidazole to essentially recover oxygen binding activity, okay? So mutated this guy to glycine, but then added in imidazole, which is essentially just the side chain of histidine to make sure that this thing was an actual binder, okay? So when they took this mutant and they exposed it to oxygen, what they found was they found that the iron porphyrin, the iron does go into the plane, right? But what do you think is not going to happen now? Because now this little side chain or this little ligand, this imidazole, is not attached to the F helix. If the oxygen, when it binds, moves the iron into the plane and that pulls our little imidazole with it, is it bound to that F helix now? What would you expect to see? This guy is not bound to our protein anymore. So do you think you're going to see that shift in the F helix? More importantly, do you think you're going to see cooperative binding? No. Okay, and so that's essentially what they see. When they replace this with a glycine that disconnects that connection between our imidazole side chain and our actual protein, they still see oxygen binding, they still see the iron moving into the plane of the porphyrin, but now that doesn't connect with the protein, and so they see a very large decrease in cooperativity and binding. Okay, so it's a nice little study that shows that there are at least parts of this model that are very correct in explaining the cooperativity and hemoglobin binding oxygen. Okay, all right, so I have a few questions. These are not on the presentation, so we're going to keep them secret. Allosteric effectors with respect to oxygen binding to hemoglobin, right? So this hopefully will give you some insight into physiological ramifications behind a couple of different other small molecule effectors that we're going to deal with in our binding to hemoglobin. Okay, so reminder that oxygen binding, changing the entire structure of the protein, making all of the other binding sites have more affinity for oxygen, that was again a very good example of an allosteric interaction, right? Where binding of one site essentially changes the structure of the protein to affect the binding at the other sites. Oxygen itself was what is called an allosteric effector. It's going to be this small molecule that binds to various sites on the protein that actually initiate these changes. Okay? So there are two different types of allosteric effectors, positive effectors and negative effectors. Okay? So a positive effector is going to be something like oxygen. So oxygen binding, what did it do to the overall affinity for the other sites? It increased it, right? So binding of one site is going to increase the affinity for binding to the other sites. There are also things called negative effectors. So negative effectors, if they bind, they're essentially going to decrease affinity. Or what we see with respect to spelling, decrease affinity. What we see with respect to enzymes is not going to be affinity for binding, but also it's going to be activity in the actual enzymatic reaction. Okay, so also we can essentially categorize these effectors as homotropic or heterotropic. So homotropic effectors are going to bind to the same site, right? This is an oxygen binding to an oxygen binding site is an example of a homotropic effector, whereas heterotropic effectors are actually going to bind to other sites on the protein. Okay, so not the actual active site or binding site of the protein. So the other allosteric effectors that we're going to look at with respect to oxygen binding in hemoglobin are going to be proton, CO2, as well as this guy, 2,3-bisphosphoglycerate. All of these guys are going to be negative effectors. So binding of these guys is essentially going to decrease the affinity for binding oxygen at our oxygen binding site. Okay, so let's start first with protons. Protons are the easiest. This is going to introduce us to something called the Bohr effect, which is essentially the effect of pH on oxygen binding in hemoglobin. Okay, so as we are respiring, as we are utilizing our oxygen in our tissues, what are we producing at the same time? CO2. CO2 first, okay? So as we respire, we're going to be producing CO2, which is a waste product, right? We have to get it out of our body some way. CO2 is also a gas, which is an issue, right? We don't want a bunch of bubbles bubbling up in our system. So what happens with respect to CO2, as we produce it, it reacts with the water that is in our blood, okay? What does it produce? If you guys remember way back in general chemistry, it produces carbonic acid, right? H2CO3, which is an acid, and dissociates into bicarbonate. Man, it's like a Monday, but it's not. Bicarbonate and proton. Okay? So as we increase the amount of CO2 that we put into our blood, in our tissues, what is that going to do to the equilibrium of this reaction? It's going to shift it to the right? And what's that going to do to the concentration of protons that we are producing? It's going to increase it, and what does that do to the pH? Right, so we're going to see a decrease in pH in our blood plasma, okay? All right, so how is that going to translate into oxygen's ability to bind to hemoglobin? So if we look at our nice little sigmoidal oxygen binding curves, and we compare what happens at something like 7.6 pH to something that happens at 6.8, what we find, again, if we're looking at just the physiological functions, so if we are at a pH of 7.6 and we are in the lungs, we'd be completely saturated at about 100 torr. As we move out to the tissues to about 30 torr, and we're at this pH of 7.6, what is our change in saturation here? So if we go from 100 to the lungs and we move out to the tissue, how much have I changed with respect to my percent saturation or fractional saturation? How much oxygen have I gotten rid of? I would say this guy's about maybe 75, so maybe 25%, right? So at high pHs, as we move out to the tissues, we only release about 25% of the oxygen. If we compare this to low pH again, pretty much fully saturating the lungs. As it moves out to the tissue, at pH 6.8, how much oxygen, what percentage of oxygen has it released when it gets out to the tissues? So this is about maybe 30, right? Goes from 100 in the lungs to 30 in the tissues. So at pH of 7.8, hemoglobin is able to release about 70% of its oxygen, right? Which is good, right? If we're producing a bunch of CO2, what does that tell you that we're doing? We're actively doing something, right? And we need more oxygen. So this is a good example of having that slight reserve at normal resting state and being able to release it when we're actively respiring, okay? That's due to this lower pH, right? We drop blood pH and we see oxygen released from hemoglobin a little bit more, okay? What does that mean with respect to which state is preferred? The oxygenated state versus the deoxygenated state, or the low affinity state versus the high affinity state? At low pH, who's preferred, T or R? T, right? At low pH, this guy has a lot less preference to bind oxygen, so it gets rid of it immediately, okay? So low pH, we have a low affinity state that is preferred. And again, that translates into releasing lots of oxygen as we move out to this low pH state. All right, so that's number one. As we decrease pH, we're going to see more of our oxygen being released from our hemoglobin. But we also have this guy, right? We have to get this out of our body at some point. Right now, it's in the form of bicarbonate, but hemoglobin and all of this relationship between pH and oxygen binding is also going to help us get CO2 out of our body, right? So does CO2, just as a note, does CO2 bind to the oxygen binding site in hemoglobin? No, right? So that's not how we're going to get CO2 out of our body. Right now, it is in the form of bicarbonate, and that's where we're going to leave it at this point in time. All right, so this effect on pH with respect to oxygen binding to hemoglobin, we can represent by this equation, all right? So in here, in front of the protons, ends up being approximately 2, all right? So what happens? We decrease pH in the tissues, and we're going to shift this reaction to the right, which essentially is going to release all of our oxygens, right? At the same time, this hemoglobin is going to pick up 2 protons. It's released all of its oxygen in the tissues. Where is it going to go next? Where does it need to get more oxygen? To the lungs, right? So this unbound hemoglobin is going to go to the lungs, where it's going to pick up more oxygen, because again, we have this large partial pressure of oxygen in our lungs. As we increase the oxygen concentration, we're going to essentially shift this reaction back to the left. So we're in the lungs, we're shifting this back to the left. It's going to bind oxygen, which is good, but what is it also going to release at the same time? Right now, it's going to release protons, right? So we're in the lungs, we're binding our oxygen, but at the same time, we're releasing these protons, okay? Going back to this reaction, our bicarbonate reaction, if we are unloading a bunch of protons in the blood in the lungs, we're increasing this guy. What is it going to do to this reaction, this our bicarbonate reaction? It's going to shift it to the left, which is going to do what? Liberate CO2 from our blood, right? So now we're in the lungs. We have essentially increased the proton concentration because we bound oxygen. By doing that, we're going to push this reaction back to the left, and we're going to get rid of our CO2 whenever we exhale. Okay, so this is a nice little relationship between oxygen binding, protons, as well as the release of CO2. There is one other way that we get rid of CO2 from our blood. Okay, so another way that we actually do it is the bicarbonate ions that are produced by CO2 reacting with water can also react with the alpha terminus of hemoglobin, right? So if it reacts with, the N-terminus on the alpha subunits of hemoglobin. So when it reacts, it forms what is called a carbamate, okay, which is this guy. Again, this is happening in the tissues. So we have bicarbonate reacting with our hemoglobins in the tissues, forming these carbamates. What's that going to produce in the process? This is the overall chemical reaction for this. It's going to produce our little carbamate, which is this guy. But what else is it going to do? It produces another proton. So every time we actually form these by reacting our bicarbonate with our hemoglobin in terminus, then we're also going to produce more protons, which is also going to decrease the pH and again release more of our oxygen binding when we're actually in our tissues. Okay, so these guys are all nice and interrelated with respect to one another. Okay, so why? Structurally, why does this decrease in pH, or why does this excess of protons prefer the T state? That's what I'm going to introduce you to next. The structural reason for why this actually occurs, why low pH has a preference for the T state. And it comes back to these beautiful non-covalent interactions that again stabilize this T state. Okay? So there's going to be one of these that is super important that you should know with respect to this mechanism. And it is, if we zoom in, it is this histidine, right? So I've told you before that histidine is going to be one of those really important side chains in essentially any type of acid-based chemistry that we're going to see, because what is the pKa of this histidine imidazole? It's about 6, right? So physiologically, at physiological pH, this could be protonated, this could also be deprotonated. So it's going to play an important role in any type of acid-base reactions that we're going to see. All right, so again, why does excess protons favor the T state? If we looked at this histidine in the R state, so the completely oxygenated version, where again, all the oxygens are bound and we've broken all of these non-covalent interactions, the pKa of this histidine is about 6.4, which is what you would expect for just free imidazole. So normal, whatever. If we're at physiological pH, this could be partly deprotonated as well as partly protonated, okay? As we compare that to the pKa of this histidine in the T state, what does this histidine actually play a role in? It forms this salt bridge, right, with this aspartate. It needs to be protonated to stabilize and form this salt bridge, right? So the actual presence of this negative charge, what's that going to do to the pKa of this histidine? So is it going to make it more acidic, so it's going to get rid of its proton and not be positively charged, or is it going to make it less acidic, so it keeps that proton and stays positively charged so it can form this salt bridge? Less acidic, right? So what we see here is the pKa of this guy ends up being about 7.9 in the T state, okay? So when we're dealing with pHs of 6.8, this is always going to be protonated, so this protonation state is always going to be preferred, and it's going to be able to form this salt bridge. Why we see this guy actually prefer the T state, the deoxygenated state, versus the R state. Because it gets to form this salt bridge, it's always protonated at this point in time, at least at low pHs. Okay, so one more. Let's talk about one more. That's the relationship between protons and binding of oxygen to hemoglobin. Our last little allosteric effector is bisphosphoglycerate. So we're going to abbreviate this guy BPG. So bisphosphoglycerate is this little molecule over here. And again, we're going to abbreviate just BPG. Okay, so what's the big thing behind bisphosphoglycerate? So if we take hemoglobin and we remove it from the blood, so we call this stripped hemoglobin, what we find is that by itself, removed from all of the blood, plasma, etc., it has a much higher affinity for oxygen binding. Okay? So stripped hemoglobin, if you look at its percent saturation curve, or its fractional saturation curve, again, at partial pressures that are present in the lungs, it's fully saturated. But now at partial pressures that are present in the tissues, if we go up here, purified hemoglobin would release very little oxygen at partial pressures that are present in the tissues, okay? If we add CO2, if we add protons, we still can't explain the actual binding curve that we get for hemoglobin that is in our blood, okay? So this led to the search for whatever molecule was causing this, and that molecule ends up being this bisphosphoglycerate. So note, overall charge, how many charges, or what type of charges do we see on this molecule? Negative. This guy's super negatively charged. Okay? All right, so we're going to explain structurally why that occurs. Also, important thing to note, BPG plays a very important role with respect to acclimatizing to high altitude. What's the problem with high altitude and breathing and releasing oxygen? Pressure decreases, so that means partial pressure everywhere is going to decrease, right? So we're not going to be able to release as many oxygen molecules if the partial pressure in our lungs as well as the partial pressure in our tissues has decreased. So what happens in a very early step in acclimatizing to high altitude is that we see an increase in the concentration of BPG in our blood from 4.6 to 7.6 millimolar, right? So the first few days that you're actually up in the mountains, you see this overall increase in the concentration of BPG to essentially try to improve our ability to release oxygen in our body. Yes?
Is BPG found in plasma or in blood cells?
I don't know. Blood cells, most likely. Erythrocytes, I think. Yeah. Okay, so, great. High altitude acclimatization. Okay, all right, so what is the structural reason why we actually see this? So one of the slides that I didn't show you before was the comparison, again, of the X-ray structures between the R state, nope, T comes first, T state, and the R state. And again, I was trying to show you how these guys structurally rearrange themselves upon oxygenation, right? So what we're looking at here is the interface between the alpha and beta subunits and the interface between the other alpha beta subunits, okay? And so again, this is our deoxygenated state, this is our oxygenated state. Note that in the deoxygenated state, there's this big open cavity right at the interface between these guys, right? What happens to that cavity as we shift into the R state? It closes, right? And so what happens is BPG comes in and it binds right at that cavity. There are a bunch of positively charged residues, as well as the N-terminus of our various subunits that line that cavity, that essentially accommodate all of that nice negative charge that BPG offers. Binding here is going to essentially preferentially stabilize the T state, right? And so when we shift to the R state, it closes that cavity and BPG can no longer bind. And so again, that's why BPG decreases the affinity for oxygen binding, right? So we see a decrease in affinity, which long-term translate into our ability to get rid of oxygen at lower partial pressures. Okay, so that is it. That's all I have. I have one question. If you guys want to take that question, you don't have to. No, it's fine. We don't need to talk about it. It's easy anyways.